Let's explore a technique which falls into the bagging technique for ensemble modeling, and that's random forest. So what's random forest? Now, the mere definition for random forest is it's basically an advanced version of bagging along with feature randomization. So if you recollect the definition of bagging, we had defined that bagging is a process where we add one level of randomization. And this one level would actually be defined in the training sample. So let's say we're creating 10 different models. Each of these models will be having a different training sample because each of those training samples will be created by taking two-thirds of the entire sample with replacement. So technically, every model learns from a different data set, and then every model will have some sort of different variance in them and kind of have a better representation of the entire data set. But random forest is an advanced version of bagging. So here we technically have two levels of randomization. So the first level is definitely in the training data set where we do bootstrap aggregation, and the second level is in the feature selection. So let's say you have 100 rows and around 10 columns. 10 columns would represent 10 features. So let's say you're trying to predict the whether a student will pass or fail in an examination, and you have a couple of independent variables. Let's say like the number of hours a student has studied for the test, his gender, age, weight, his background, educational background, and his income level, and so on. So let's say there are 10 random uh, features associated in this use case. So what would random forest do? Random forest, let's say we're creating five different trees. It adds randomness first in the training sample. That's done. Secondly, each of these trees get a different sample of features for training. So let's go to the visual tool. So let's say we have three different models. So we have T1, we have T2, and we have T3. So the first level of randomness is in the training sample. So let's say out of 100 rows, 65 goes over here, 65 goes over here, 65 goes over here. And each of these training samples will have 65 which don't overlap. So if you technically look at these training samples, they might overlap, they overlap, but then to a certain extent. It is not a complete overlap. Now the second level of randomization is in the feature selection. So let's say out of 100 rows, you have 10 columns or 10 features. Now out of these 10, you randomly select any 4 into this. Now 4 is a number which is predefined. You can actually increase this number, decrease this number. But then out of a ballpark number to actually select would be kind of a square root of the number. Let's say you have 10, so square root of 10 would be, let's say, approximately 3. So you can choose either 3 or 4. Like 3 or 4, either of them would be fine. Let's stick around with 4. So T1, which is the first tree or the first model, gets first a randomized input, which will be different from all of the models, and it also gets a random set of 4 features from the available set of 10 features. Similarly, T2 also gets a randomized input, and then it gets again random 4 input features. Now, again, similar to the trained data set, 4 features over here, 4 features over here might overlap. Let's say 2 of them actually overlap, but then definitely it won't be a scenario where both the trees are completely same, like in terms of features or in terms of the training data set. So what we do is we impute randomness in each of these trees to the next level. The first level is in the training data set, so the learning process for each of them is different. And the next level would be the feature selection. So let's say tree 1 might learn the probability of a student to pass or fail as a function of gender and weight. Tree 2 might learn the probability of for the same use case as a function of the number of hours he studied for and the number of and his educational qualification and so on. And this process goes on. So each of these trees has, apart from the training sample, which helps it learn in a different way, also has a different structure or a solution space when we have accommodated randomness into the feature selection process. So that's random forest. At the end, you combine results from all of these models into a single model using voting. So let's say the first model said yes, second model said yes, third said no. The net result would be a yes. That's random forest. Let's come back to the nodes. So we say random forest is an advanced version of bagging along with feature randomization. What does it do? What is bagging? Bagging is an ensemble of decision trees with bootstrapping. What can we do with random forest? It can do classification as well as regression. And what's different in a random forest? So random forest is more robust in generalization and regularization. It's kind of less prone to overfitting. It's less prone to outliers, and it is relatively easier in tweaking and tuning the model. So one of the most widely accepted models in machine learning frameworks is random forest. It's relatively easy to build. It's blazing fast because you can do parallel processing over here, and you don't need a lot of math in the background. You can kind of abstract stuff and still have a relatively good amount of accuracy. Now we'll come back to another important discussion. When would we use random forest, right? So we discussed about bias variance trade-off. You would have a scenario where there's high bias or there's high variance. When do we use random forest? Now, you would either have high bias and you would or either have high variance. If you have both of them, it's kind of a very complicated scenario. But then you would use random forest in one of these specific cases, either when you have high bias or when you have high variance. If you look at the kind of explanation that we have discussed till now, like random forest helps bring some sort of randomness across different models. So what would it actually reduce? Will it reduce variance or will it reduce bias? Take a call. This is an important thing. Technically, when we have a scenario where things are overfitting, so when you say things are overfitting, you technically have high variance. So you'll have exceptionally good performance on your training data set, but then you'll have very poor results on your testing data set. So that's a scenario where you're saying overfitting. So random forest can actually be used to reduce overfitting because it kind of generalizes your model in a much better way. Similarly, when you have underfitting, that is a scenario where you have a lot of weak learners. So you have a model which is kind of poorly performing on your test data set as well as your training data set. That's when you will ideally use boosting. So you're combining several weak learners into a more powerful learner. That's boosting. So just as a recap, for random forests. Random forest is again, as you know, it's an ensemble modeling technique. It is basically an advanced version of bagging where we have the next level of randomization introduced in feature selection. We can actually do prediction of classification use cases as well as regression use cases. And it's generally known because it's more robust because it's less prone to outliers and you can easily tweak and tune the model. So that's random forest. Let's have a look at boosting for XGBoosting.